Now we're ready to move to our next chapter, which is the main focus of this lecture today, presentation of technical information. So again, we're still in the engineering method. We're still in the way of proposing what you found in front of an audience. Either that audience is a public audience, or is it an engineering audience? It's your upper management, it's the university, anybody else who's interested in the findings that you found in your solution. And I believe you can relate back to the design process. At the end, you end up with communication and documentation. And part of it is presentation. Either you present it in a Zoom meeting, or you present it in a PowerPoint or in a PDF report. You need to present it in a kind of generally accepted way in front of people. Now, the objectives of this chapter would be, first, we will try to learn how to recognize the importance of collecting, recording, and plotting, interpreting technical data. As an engineer, you are in the field, you are in the lab, you are in a vehicle, whatever you're doing, whatever your main focus, you will be collecting a lot of data, and your profession as engineer, make sure to read that data properly and express it to the right audience properly. After that, you would be able to do some analysis to let the people who are not well familiarized with your science to be able to understand what this data is about. The second objective, we will practice the methods of graphical presentation of our scientific data and graphical analysis of plots. Then we will be able to develop the ability to graph the data, and we will determine the right type of curve to be able to use in our presentations. There's many types of curves that we can use. Some of them are useful for some type of reports. Some of them are not. So you want to be able to know what type of graphs we have or curves and use the right one for the right purpose. Now here we will take a kind of explaining example. We have 3 engineering students. They need to study the effect of altitude and temperature, like the effect of amplitude on temperature and pressure. Now what they did, they rented a helicopter for half an hour and collected the data manually. Let's say they distribute the work, like somebody would be registering the height based on the information from a helicopter. The other student would be recording the temperature. The other student would be recording the pressure. Now at height 0, before they launch their flight, temperature was 59, pressure was 14.7. Now we said height, temperature, and pressure. What is important in this table to be written to be able to get the best out of it when you go back home or when you land? So we have a table. In it, we have height, temperature, and pressure. Now you'll start to write stuff. What is a crucial information here to include other than that? Forget about how they graph it. Units, exactly. Yeah. So units are important, and abbreviation of your parameter is important. If it's an abbreviation that's known for all the scientific or engineering field and professionals, then you know that T, it's almost universal, that everybody knows T stands for temperature. So you use the right notation for the right parameter. Here we have height, H, and the units are feet. Some people use meters, so you need to be specified about it. Maybe when you go back landing, you forgot what units you used for, unless you're using a device or something. Then for temperature, we use, in this case, Fahrenheit. For pressure, we use pound force per inch square. That's something just to keep an eye on, because in engineering, there's a lot of application and a lot of engineers who use metric, including myself. So you will see a lot of metrics and other units, SI units, and stuff like that. Okay, so these students, they collect the data manually, and they try to plot. Always, what's the next step after collecting data? You got to plot something, either manual or using the computer. When you plot stuff, you'll be able to see how is the progress going. You see what we call it as a trend, what is going on with the data, and be able to draw a conclusion. As I'm going to mention moving forward, human being is a visual creature. So you love to see things. As you mentioned in the first of the lecture, you love to see things. Seeing is believing. So without seeing stuff, it's hard, unless you are a genius in math, it's hard to, even you still slip it because it's hard to visualize numbers, but you can visualize it using graph. Now here what he did, kind of weird graph. It's not an XY explanation here. So we have the height on the x-axis, and we have the temperature on the y-axis, and on the y-axis on this side, we have the pressure. It's kind of a three-sided graph. Now he go at height 0, what was the temperature? Maybe 55 or 60. Now at height 0, what was the pressure? Then you go according to the pressure and put the point relative to that. Now drawing the points, you can see here this is a legend. Maybe it's not very clear for you. So there is a dark dot and there is a hollow dot. Dark dot is pressure, I believe. Hollow dot is temperature in this case. So you can see how pressure is doing versus temperature as the height increase. So how are we going to read this? First, how are we going to design it? We will learn. We need always to have a legend. You need to tell me what this black dot means, what's the hollow dot means. You tell me that in a legend. That's what we call legend. And if you're using color codes, in your legend, you should have the right color code. More essential than that, when you first draw your two lines, on x-axis, you need to tell me what is the x-axis is about. What is it representing in this case? We are representing height. Then you give me the abbreviation for height and the unit. That's required on any plot. Then for the y-axis, you tell me what it is. It's representing temperature, abbreviated as T in Fahrenheit units. After you define the axes and you try to have the title of the axis as centered as possible whenever possible. Here it's not very centered, but you know it is the tag or the title for the axis. And you have the legend. You draw the data and you need to tell what's the conclusion. Like if you're using each data set having a different logo, then you're gonna tell that in your legend. And you're gonna give me the title of the graph itself. What is it representing? In this case, it is the data collected for heights versus temperature versus pressure. Now that's what they did by hand. But when they landed, these students, they went to the lab and plugged in their data into an Excel sheet, as we can see here. So after, in case you are collecting the data manually, the first next step after doing that and graphing manually, you should be able to go to the computer as fast as possible and plug in the data into the computer. So now what's the plot purpose? It is difficult for humans to observe, as we mentioned, by numbers and see the trend. You gotta go through the visual. You gotta see to be able to describe what's going on here, as we are visual creatures. So when you see here, you know that on x-axis months from January to June, then you have on the y-axis number of bicycles sold, and you see the trend. Okay, in January we had 50, then they got less, they got higher, less, and finally they matched the first sales amount that they did at first. So you are visual, you are easily to see stuff visual, and as you're communicating with other engineers or other scientists, then you are able to let them visualize what's going on. Now, plotting softwares, we just talked a little bit about how to use Excel. You can always plot by hand. But of course, as I mentioned, it's more efficient and flexible to use plotting software to do that. In the industry, in the market, you are expected to use softwares to do that. Now, plotting software, what's good about it? It gives you the ability to generate accurate and nice looking graphs. You can play with colors, you can play with shapes. As we just saw, we can create two y-axes on both sides, and we can change the color of the bar and the legends and all that stuff. Now, plotting software is available in the market. Excel, of course, not the best. We have MATLAB. There's a lot of ways to plot stuff in MATLAB, but it's more technical, as you know from your MATLAB experience. Then we have as well another MATLAB competitor, which is Mathematica. You can use MathCAD. Something more commercial, Power BI by Microsoft. Go ahead and look up Power BI and Tableau. Those two are kind of trending in the market. Like today, the people who are presenting data, let's say for the stock market in New York, mostly they're using Power BI and Tableau. What's the beauty about Power BI and Tableau? They are more graphic focused. They can manipulate your data, but they still make your data looks awesome and eye-catching. So look them up, see some samples out of those. For collecting and recording data, we have the manual way. Well, as we mentioned, if you want to go with the manual way, it's very preferred that you use the tabulated notebook for your data entry to be able to enter the data in an Excel style, but in a manual way. Write down your testing date before you start, the location of testing, the type of equipment you use. Like you enter in the lab today, you have a computer, there's a Windows-based computer, and the date today, the time today is this and that. And you say what type of equipment you're using. That's very important when you're in a lab doing some scientific or engineering research. It's important to know when you entered the lab. So when you come back a month later with 1,000 data sets, then you will be able to tell which is which, who is who, what kind of equipment you used. Record as much data and observations as possible. You know, as you are doing your testing, we are saying here scientific testing. Let's say you're a researcher somewhere. It's important to say, okay, I observed when I increase the temperature, there's a spark coming out of that material, for example. It's good to have your note, what equipment you use, then you decide if it's just a bad data, malfunctioning in the machine, or is it really something, maybe you find out a new material in your life, you never know. Then when entering the data point that you are not sure if it's accurate or not, then you exclude it. You don't include it and we see later. Of course, there's a lot of outliers in your graphs, but there's an organic outliers and there is a kind of worker error outliers. So you want to exclude any bad point that you felt when you did the experiment. You thought, well, I think I did something wrong. I'm sure, I'm almost sure. So you got to exclude it, don't include it. Now, when you exclude the data point, cross on it, but don't delete it, because you could come back and say, oh, no, I think I did what should be done, then why did I delete it? So it's always good to keep the door open behind you. And you need to take your time collecting data and writing your data. Never rush collecting data and doing experiments, because you're going to increase the possibility of making errors and mistakes while recording the data. Now, it's more simple using the software. As you know, in the market today, there's many automated data collection hardware and software available. As an example of that, there's in the market LabVIEW. That's a software you connect with a lot of hardware. And there's as well, let's say, PLC automation. Many of the automated factories out there in the market are being programmed through the PLC ladder program. And they're having Allen Bradley hardware. And those are having their own, what they call National Instrument data collection machines. So they collect the data for you. You have a pressure sensor somewhere, you're going to collect it for you as the period you want it, at the timing you want it. So it's pretty automated. And laptop or tablet can be used for input or analysis whenever needed. Now, if we want to take the graphing procedure in terms of steps, first you select the type of graph paper. In case of manual, you choose the right location for horizontal and vertical axes, determine the parameter and units for each axis as we learned. Then we grade the axes, means 0, 1, 2, or 10, 20, 50, 60, and so on. Then you want to identify all grades and components of the axes. Then after that, when your axes are ready, you start to plot your data points and symbols as needed with a legend describing which is which. Now you check outliers, which means all the data falling out of what's expected. Draw your curve, identify each curve, add title, include needed callouts and notes as needed. Then you need to make the graph aesthetically pleasing and readable. Now that's the kind of paper you use. I believe you know it from your math, right? So there's the log paper where it's not homogeneous, as you can see, the lines, the squares are not equal. One, there's the standard, or there's a Similog, and there's a standard. There's a third one should be here, which all the squares look the same. Now, as we said, there's coordinates, and there's your boxes or squares, if you will. That's your graded paper. It makes it easier for you to draw down the points. Not necessary, but it's good to have it in case you're doing manual. Then there's a coordinate axes. Now, there is something called axis breaks. Let's say your data from 0 to 80, there's no data there. There's no point to draw that scale. So I make like kind of a zigzag, that's the mark you see here. So that's telling you this is a continuation, like we skipped many points and we started at 80. We skipped many points and we started at 60, because in this area, if I draw it just too big in the paper that I'm drawing, and there's no data just starting from 80, that's where my data. So it makes sense to start from that point. There is the uniform and the non-uniform scaling. You gotta be always calibrating scaling. If you do manual, make sure 0 to 10, same distance as 10 to 20. So you need to have it in the right grade. Now, acceptable versus unacceptable scale graduation. In A, we have acceptable graduation where each mini point, or let's say a mini grade over here, is representing a certain number that equal to the next mini grade, and so on. In this case, we have 0, 1, 2, 3, 4, all the way to 10. So we have 10 mini grades before we reach number 10. And the unacceptable graduation, let's say you go from 0 to 10, but you have, if you want to split it on these two mini grades, that's going to be 3.33 each, which doesn't make sense and make just life more complicated. For time as a variable, let's say you represent on the x-axis time. You can go Sunday, Monday, Tuesday. You can go July all the way to June or to December. You can go with years. You can go either you put years from 1980, you put it the whole thing, 1980, then 81, 82, 83, so we understand you talk about years. Or you can have it always complete. Honestly, most graphs I ever see having the full year. Don't go with the 1980, then 81, 82. It's just showing you as too lazy and give a bad impression about you. Scale calibrators, you always need to have your scale readable. So don't get numbers too close to each other. I believe in Excel you can spread them out easily. Don't get it too crowded, always readable. Keep in mind you print the page in A4 size, somebody else could print it in A3 size or smaller size. So things could be squeezed to him. So you're going to be able to read it all the time. Now, the proper representation of data, we have either true slope or expanded y-axis, or expand y-axis in the horizontal direction. Just different ways to show your data, but what I'll tell you, always care about having the data clearly noted out on the graph. Have a legend to tell what kind of symbol you use to represent each data point. Reading the scale is important. You need to know what each mini grade means. Of course, you always have the axis name, abbreviation, and units. Axis labeling, one more time. Each axis should be clearly identified. Axis label should contain variable name, symbol, and units. Label should be parallel to the axis and centered. Not necessary, but it's just more aesthetic if you can make it. Like distance in this way, the word distance is same as what I did on the side. This is not the best way. If you can make it parallel with the y-axis, that will be just looking better, if that makes sense. Now, plotting data points. You are plotting points that are observed. Those are usually plotted with observed data points connected by a straight, irregular line segments. Line does not penetrate the circle, so the circle will be an overlay above the line. You could have empirical, where reflect the author interpretation of what occurs between the known data points, which is a trend in this case. And you could have as well theoretical, which is a graph that have a certain curve into it. You don't show data points as dots, but you show the general curve of a function, let's say. Symbols, there's all kinds of symbols. You can explore that in Excel, in MATLAB, any software you prefer to use. Use any symbol you want as long as it gives beauty to the graph still. And you can have it listed in the legend. That's what we care about. Line type, you can have dotted, you can have continuous, thick, and thin lines. You can see here different symbols for different data sets. When you have pressure, temperature, and height, it's never use the same symbol. Even though I prefer, even if you change the color, like for triangle for pressure, don't go with temperature, have a triangle in red. Because if somebody printed in black and white, you gotta be considerate about that as well. So have always different symbol for different points and different parameters. Now the graph types, we have the pie graph, and we have the bar graph. This bar could be, like the bars could be standing, like, you know, it would be standing, or it could be in a horizontal format. Honestly, this kind of bar style is more famous. Like you have the bar standing instead of having it horizontal. So this one is more famous. We have the column representation, which is, yeah, that's what I just said. Then you have the line where you have dots connected. You have the area. Like this line, if you draw the area under the curve, that would be an area. Then you have the donut representation, very famous for infographics. Whenever you need to have your graph look pleasing and nice, you could use that. You have the bubble chart. I never did use it. I don't think it's useful. Then you have the spider and radar, not very useful unless you're working with vibration area. Then you have the scattered dots. Like the dots is scattered, no lines in between. Then the list formal charts comparison chart, where you have lines of information. Then you say, okay, let's say your attendance sheet. Then I say, okay, a dot means he attended. Nothing means he's not there, or X, he's not there, and so on. Stacked bar chart, so you can have the purple represent a certain parameter, the red something else, the green something else. Then you have the gauges. We use that more in lab view, where you represent the speed of the engine, speed of the vehicle, and so on.